Okay, so in this chapter, we are going to talk about both exponential and logarithmic equations. Okay, so some of you are remembering things from last year. Okay, this is going to be a very familiar chapter, which is why I make it so short. We're going to fly right through it. Okay, we'll spend the time we need to, but I don't know how much new material. We'll do a little bit of new material, but we have to do some recalling first.
What's going to be the first chapter that is all new?
Probably when we get to matrices.
Like, good job. We did that.
What?
Mm-hmm.
Yeah. Well, we're gonna do a lot with matrices that you didn't. Well, it'll be like one section of review then, and then the rest of the sections you won't know. Okay. Second quarter. Don't you worry. Okay. Second quarter. Okay, so an exponential function, and that's what pre-calculus first semester is kind of strange, because we do things that we did in Algebra 2, but we build off of them. I mean, there was a lot on your test that you didn't do last year in Algebra 2, but we had to, like, remember the basics to do the more intense stuff, right? So an exponential function, okay, we have a number raised to a variable power, okay? So a polynomial, we have a variable raised to a number, right? Now we have a number raised to a variable power. Okay. Today, we are going to talk about what their graphs look like. We're going to talk about our parent function transformations with how we graph them. And then we're also going to talk about compound interest. Okay. So we're going to talk about two parent functions, and what we talk about with these two parent functions are things that I will ask you on any of the other graphs. Sun's not shining pretty bright. We're gonna. Okay, so a to the x power is going to look like this. It'll just be more or less steep depending on what a is. Okay, 2, 5, 7. What number can a not be? 1. 1 to any power is 1. Okay. Also, yes, 0 would not make sense either. Okay. All right, but here is our graph, right? Callie, well, how would you describe the domain? All real numbers. Okay. We do have an asymptote here at y equals 0. Okay. Since that's the case, Tegan, how would we describe the range? Everything above 0, so 0 to infinity. Okay. Our y-intercept is going to be 0, 1, because a to the 0 gives us a value of 1. That will change if there are any shifts or stretches. Okay. Now, what do you notice about this function? It is always doing what? It is always increasing and never decreasing. It is exponential growth. It is always growing. You talk about exponential growth in science class? Yes. Bacteria grows exponentially. All right, if we make this a to the negative x, what's going to happen graphically? It's going to always decrease instead. A to the negative x. Everything looks the same except we have that reflection. And now we have exponential decay. Okay. So when we have a positive exponent, we have exponential growth. Negative exponent, we're going to have exponential decay. Okay, so our domain is going to stay the same. Our range is going to stay the same. Our y-intercept is the same, except now we are always decreasing and never increasing. Okay? Exponential decay versus exponential growth. All right, so we're going to go through a parent function, and I want to explain to you what I expect from you from a graph, okay? In this chapter, there are going to be things that I want you to do with your calculator, and there are going to be things that I want you to do without your calculator. So both our quiz and our test are going to be calculator, non-calculator assessments, okay? So graphing an exponential function is something I would like you to be able to do without your calculator, okay? So we're going to go through the parent function, f of x equals 3 to the x. And what I'm going to have you do, I'm going to have you pick the same 3 points for every graph. And you're going to see a pattern, and they may be the same 3 points you did last year. I am not sure. But what I want you to do is plug in -1, 0, and 1. Okay. Let's talk about these coordinates. What is 3 to the first power? What is 3 to the 0 power? And what is 3 to the negative first power? 1/3. Okay, those are 3 easy points to think about. Okay, you don't have to put a lot of strain on your brain to come up with those 3 points. Okay, it gets us what the parent function of y-intercept is: 1, 3, -1, 1/3. Okay. The parent function will always have an asymptote at y equals 0. Which it will approach to one side. Let's think about why a graph a to the x power would have an asymptote at y equals 0. Nick?
Anything to the 0 power is 1.
Anything to the 0 power is 1. Okay, but why would we not be able to have any coordinates on or below the x-axis? Great.
Because if you're doing anything to any degree, you can't have it. There's still going to be a value that isn't 0.
Okay. So we're taking a number to a power. Even if we're taking to negative powers, we're getting fractions out of the deal, right? Is there any way we can take a number and raise it to a power and get a negative number out of it? Okay? Yes. You raise negative, but that's one of our stipulations, right? A can't be negative. Okay? Exactly. Okay, it's the same thing. We can't take anything to a power and have it be 0. So we have this asymptote kind of guarding that because we know that there are not going to be any values that would meet that stipulation. Okay? Let's go back to our transformations of functions. Okay, let's flash back to chapter 1. chapter 1 when we did function aerobics and the transformation of functions. Okay, I'm not going to make you do function aerobics again, but we need to be able to remember how A, H, and K affect our graph, because we're going to use those to help us. All right. So A, Tiger, what does A do? Okay, what kind of stretch or shrink? Good. H. Keegan, what do you think? Okay. It's going to be a shift, right or left. And then K. Lindsay.
We're done.
Okay. So what we're going to do if we have a graph that has more than just a to the x, we're going to think about the graph of a to the x and then use our knowledge of transformations to shift those. Okay? It's not always going to be to our benefit to take -1, 0, 1 if we're not thinking about the parent function. So I want you to think about the parent function and then take those points and move them. That's why we worked so hard on the transformations. Okay? So we have already found the parent function for 3 to the x power. Okay? Now we're going to go through a couple graphs like this one, 3 to the x plus 1. Go ahead and write it down. Okay. What I want you to do when you graph these is I want you to think of the parent function, 3 to the x. Okay, we've already done that, all right? But the -1, 0, 1, I want that to be plugged into the parent function. So 2 slides previous, we talked about how we had the points -1, 1/3, 0, 1, and 1, 3. Okay, now let's think about the function that we really have, 3 to the x plus 1. Okay, Caleb, what is that 1 doing to our graph? It's going left 1, okay? So this is a shift left 1. So I'm going to make a new XY chart where I take these points and I shift them left 1. So instead of -1, 1/3, I'm going to have -2, 1/3. And instead of 0, 1, I have -1, 0. And instead of 1, 3, I have 0, 3. Okay. We will still have the asymptote at y equals 0. Okay. It's just our parent graph shifted to the left one. Okay. Maverick. Oh, I am sorry. I graphed it that way, but I wrote it. Thank you. Okay. Now, some of you will write both of those charts down. Some of you will just write the one in the red, okay, which is the one that I do want. But I want the parent function to be your first thought, and I want you to take these points and I want you to move them however you need to. Okay. Okay. Let's talk about this one. Okay, so with all your graphs, I want you to think of your parent function first. I picked the same parent function for all of these couple examples, okay? So our parent function is still the 3 to the x power. Okay, so either written on your paper or in your head, doesn't bother me either way, I want you to think about these 3 points for our parent graph. Okay, then we can consider what's going on with our equation, that -2. Liam, what is that doing to our graph? Okay, so for 3 to the x minus 2, we have to shift down 2. All right? So -1 1/3 becomes -1, -1 2/3. 0 1 becomes 0 -1, and 1 3 becomes 1 1. Okay. You can do the shifts numerically or you can do them graphically, okay? Whatever works best for you. I know some of you like to think of it numerically, as in like subtracting or adding certain numbers. Some of you like to do it visually, where you find the parent function coordinate and then count however many you need to in a certain direction. Okay, it doesn't bother me either way. Now, here is my question. Do we still have an asymptote at y equals 0? No. Haley, where would it be?
-2.
Okay, since we have a shift down 2, we also have to shift our asymptote down 2. Okay, let's talk about how that's going to affect our domain and range. Okay, is our domain changed? No, your domain of any exponential function will always be all real numbers, okay? No matter what. All real numbers. What's going to be different is the range, okay? Marissa, what do you think the range would be? So our range is going to be -2 to infinity. Our range is going to be affected by where that horizontal asymptote is. Okay? In this case, it's everything above the horizontal asymptote of -2. So -2 to infinity. All right, we're going to do one more graph because I want to talk about one more kind of transformation that we really haven't yet. And then we will move on to a couple other things. -3 to the x. Okay, we're still going to think about our parent function. We plug -1 0 1 in for the x's. We get our y values for the parent function. But that negative out in front of our function, what is it doing to our curve?
Changing all the y values.
It's changing all the y values. Caleb, you did something with your hand. Flips over what? Okay, a negative out in front of our function is going to flip all of these over the x-axis. So since there are no shifts, specifically vertically, we still have y equals 0 as our asymptote, but that negative with the x is going to flip all of our y values to be negative. So instead of -1 1/3, we have -1 1/3. and 0, 1 becomes 0, negative 1. 1, 3 becomes 1, negative 3. Okay, so the domain, like I said earlier, always going to be all real numbers, but our range, because we have a transformation, could be different, not always, but in this case, our range would be A. Where do we have Y values?
It'd be like, it's over the negatives.
Yeah. Okay, so where do our Y values like get cut off at? Okay, so it's everything below 0, right? So we'd say negative infinity to 0, and since we have that asymptote, there wouldn't be anything at 0. So you have the right idea. All right, what I'm going to do on the next slide, I'm going to put up a parent function of 4 to the x, and then 2 functions that have been transformed. I do not want you to graph these, but what I would like is for you to describe the transformations of 4x to the x minus 2 and 4 to the negative x plus 3. Write down what you think the transformations are, and then I want you to check in with your neighbor to see if you have the same thing. I'll give you about 30 to 45 seconds to do that. I haven't heard very many voices. Make sure you're checking in with your neighbor.
It's the non-stop. You're right.
Nope, you're right.
Come on.
You love him. And it's good to be with you.
It's a rare occasion.
All right, first one. Eli.
Right to
Do we agree with Eli? Okay. Kira, the second one.
Reflecting the horizontal and
And then up 3. Okay, so this reflection causes it to be exponential decay, right? That's what she meant by horizontal. And then we have a shift of up 3. Okay? All right. We need to talk about a number that you know, but the number E. Call it the natural base. Did you have a question?
So unlike the last one with the negative x,
Uh-huh.
so that's not a reflection in the y-axis.
Yeah, and what she said is horizontal, which is the same thing as reflecting over y-axis.
Is the y-axis vertical?
But when we reflect it, it's the horizontal values that change. Okay, so when we reflect about the y-axis like this, all of our x values change, which is why she described it as horizontal.
Okay.
Okay. All right, so the number E. It gets confusing, right? Like we have all these variables, and now here's a letter that's a number. Okay? We call it the natural base, and it is the most important base. Do you know why it's called E? Yeah, it is actually not for exponential, but that was an excellent guess. It is Euler's number. E-U-L-E-R. He got to name a number after himself. He is that cool. Alright. E is an irrational number, just like pi. What is it, Caleb? You know it?
2.7,
Nice. Okay. 2.718281. So I always say every year, like we need to celebrate E Day and Pi Day. Like February 7th, right? We can celebrate E Day.
yes.
You remember that? Okay. Go ahead and get out your calculator and see if you can find it on your calculator. Most of you have new calculators for the year. On the TI, it is probably probably one where you have to press like seconds to
Right
get to
here.
it.
Like E to the X.
Yep.
E to the X.
Yeah, it'll be the E to the X button, and then if you just want E, you put an E to the first. It should be wherever the LN, natural log button is. Raise your hand if you can't find it. Everyone put an E squared. Just make sure you know how to use your calculator. Okay. Now, you may have a graph in your homework that's like e to a power. You are allowed to use your calculator because e is an irrational number. You're not going to know what e to the negative first power is. But any of the other graphs you do need to do without. Okay. Now, how can e be helpful to us? Okay. I'm going to give you two formulas, and you should recognize these formulas. Compound interest. I'm just going to give you both of them at once. Okay, so PERT, you recognize.
Name my pet
And PERT is helpful in science class too. I want to be specific that what we do in here, we're going to use time as in a number of years. Okay. So notice how these two formulas have the same variables, except there is an N in the first formula where there is not in PERT. I also want to point out that the amount is going to be after T number of years. So it's not, you're gonna have problems where you're solving for the amount, but these first introductory problems, we're gonna be solving for the amount. So we're gonna principal. Who can describe principal to me?
initial investment.
Okay, that's your initial investment. The rate is how much you are either gaining or losing. Okay, if you're depreciating, you would have a negative rate. If you are accumulating, you're going to have a positive rate. Okay, you're going to get rate as a percentage, but we know that percentages are written as decimals, and you'll need to make that connection when you use the formula. Okay, time is in years. Over here, okay, if we compound so many times per year, it gets compounded monthly, it gets compounded quarterly, whatever. If it's quarterly, that's 4 times a year. If it's monthly, that is 12 times a year. Okay? Where over here, if you see the words compounded continuously, that means it is always being recalculated, and that's when we use the E. Okay? PERT is when we are using continuous compounding. Okay? So here is a time where you really need to read carefully and pick out the correct pieces of information so that A, you know what formula to use, and B, you can use it correctly. All right? So, a total of $12,000 is invested at an annual interest rate of 9%. Find the balance after 5 years if it is compounded quarterly and if it is compounded continuously. Yep. Okay, so I'm going to underline some things. $12,000 is invested. What does that mean? That's the principal. Fee is $12,000. Okay? At an annual interest rate of $9,000, you are always going to see annual interest rate. That means the rate doesn't change over the course of the year. Okay? So our interest rate is 9%. What does that mean R is? 9.09. Find the balance after 5 years. What does that mean? Time is 5. Okay? Now, here, since we're being compounded quarterly, that means N is going to be 4. All right? So, if we go to use this formula, our amount equals principal times 1 plus our rate over N times NT. Oh, N is actually a number here. Sorry. You have very nice calculators. Please do not pluck one calculation at a time to figure this out. We can put it in all together, okay? You can type in 12,000, and then you have parentheses, and you can type in 1 plus 0.09 divided by 4. And you can raise that. If you have a TI-84, you can take that 4 times 5. If you have a calculator that does not give you that exponent box, you would need to put your exponent in parentheses, or you just have to do that calculation of 20, which you can do. in your head. Okay? So if we invest $12,000, then after 5 years, we would have $18,726.11. Woohoo! Whoops. I got so excited my marker went in the trash can. Okay. Now, compounded continuously. What's going to change here? We have 12,000 e to the RT. Same thing. Use your fancy calculator. Okay. 12,000 e to the 0.09 times 5. Like I said, if you don't have a calculator that gives you the little exponent guy, then you need to put your exponent in parentheses. Okay, why is this amount larger? Okay, the more times you compound, the more money you're going to make. Okay? The higher the interest rate, the more you're going to make. The more it's compounded, the more you're going to make. Okay? Things to think about. Now, if you are paying a loan, do you want a high interest rate that's compounded a lot? No, because you don't want to pay as much, right? You want the opposite to happen. Okay? All right. We have 2 minutes left, and so I'm going to go through a bonus example of the first kinds of problems you're going to see in your homework, okay? Is that okay with everyone? It's not like you're going to start your homework right now anyway. So write this down because you have it on your gold sheet. I gave you your gold sheet, right? Okay, if I wanted to do this problem right here. Okay, Caleb, what would you need to do?
Okay, you have to do the 8, you have to make it 2 to the power or something.
Okay, we need to write these as the same base. So 8 is the same thing as 2 cubed. Do you agree? So now we have 2 to a power equals 2 to a power, which means what should be true? Your powers better be equal. And now you have a nice linear equation to solve. All right. Reference your gold sheet for your homework.